In this lecture, we're going to take a look at vector-valued functions and the calculus of vector-valued functions. Previously, you defined a plane curve as follows. Is the set of ordered pairs so that x and y are both parametrized by functions in terms of t. And this gives us an ordered pair where the x is given by f of t and the y is given by g of t, where both f and g are continuous. We can extend this definition further to space so that in R3, a plane curve or a space curve, as it sometimes can be called, is the set of ordered triples x, y, and z, where x is equal to f of t, y is equal to g of t, and z is equal to h of t, where f, g, and h are continuous functions of t on some interval. Using these definitions of plane curves, we can define a new type of function. We know that points more or less are going to define vectors, and the terminal points of vectors where the initial points are starting at the origin. And so the new type of function that we are going to define is the following. A function of the form r of t is equal to f of ti plus g of tj, alternatively could be expressed as f of t, g of t. This will be another name for r of t. Or r of t could potentially be in space, so that we have f of ti plus g of tj plus h of tk, which can similarly be expressed as r of t is equal to f of t, g of t, h of t. And these would be describing vectors, and so these are what we would call a vector-valued function. where the component functions f, g, and h are real valued functions. Note that in this case we are omitting the information of f, g, and h being continuous. This is because you shouldn't confuse a vector-valued function with a plane curve. While they do produce a similar graph, a vector-valued function need not have continuous functions for f, g, and h, whereas if we were describing a plane curve, we would necessarily need continuous functions. So we should also take note of the fact that the plane curve is the set of points. Or the connection of all the points. Whereas the vector-valued function is the terminal point that traces the plane curve. In 2-space, if we had a vector-valued function given by r of t is equal to some f of ti plus g of tj, what we are describing in essence are the vector-valued functions that have a terminal point on the plane curve. One could also define something similar in R3. One notable point to make is that plane curves and their respective parametrizations induce an orientation on the curve. That is, when we make the connection between all of the points of our plane curve, we do so in a specific direction, and that's in the direction of increasing t. And so however we draw our plane curves that have been parametrized, we have to also indicate the direction in which the curve is traversed. So let's take a look at a few examples of parametrized functions and vector valued functions in the context with plane curves. So suppose that r of t were to equal the sine of t, I, plus the cosine of t, j. If we were to try to plot the plane curve represented by this, the plane curve would have coordinates sine of t, cosine of t. And so in order for us to be able to determine the x and the y coordinates, we should necessarily make a chart of values. Now, we know that this is going to look like a circle in the end. How the circle is traversed is the question. Are we going to do it in the counterclockwise direction or in the clockwise? So starting at t equals 0, if I were to put this in, I would get that the x value is going to be 0 and that the y value is going to be 1. And so in our graph, we would be starting at the point 0, 1. We would then probably go to pi over 2, and in which case we would go to the point 1, 0. And so we would see that our circle would be traversing the path of increasing t in the clockwise direction. The arrows that you draw should indicate in which way the curve is being oriented. You can get the same graph and the same orientation through a different parametrization too. For example, if r of t were to equal sine of t squared, I, plus cosine of t, j, cosine t of squared, j, this too would also produce the same graph. You could get a different orientation for your graph if you were to switch the cosine and the sine, so as to say r of t is equal to the cosine of ti plus the sine of tj. And remember, when we're talking about these functions, these are not, the plane curve is only the set of points connected. The actual function itself are going to be the vectors. Since this is a vector valued function, it's going to be the vectors whose terminal points lie on the curve, and those vectors are going to traverse the curve in the direction that the arrows along the curve show. So, for example, in the case of this function here, we can make the following table. Starting with t is equal to 0, we would see that when I plug that in, I would get 1, 0. And if I were to put pi over 2, this would shift it to 0, 1. And we know that this is going to be the graph of a circle because we have done this before in a previous class. And the graph of the circle is going to be traversed in this case, since we're starting at 0, 1 and going to starting at 1, 0 and going to 0, 1. We are now going in the counterclockwise direction, and the direction that the vectors are going to traverse are going to mirror that of the plane curve itself. And so those would be some examples of plane curves and the relationship they bear with the vector valued function. The domain of a vector valued function given by R is the intersection of the domains of the component functions. F, G, and H. What that means is I need to find the domains of f, g, and h respectively, and then determine the values of t that each of those domains have in common. This is best seen through example. Suppose r of t were to equal the natural log of ti plus the square root of 1 minus tj plus tk, and we were asked to determine the domain of R. This is going to require us to find where each of the functions is continuous and to consider each one separately. So for example, if we have f of t is equal to the natural log of t, this is going to have a domain of 0 to infinity, not including 0 because the natural log of 0 is undefined. For g of t, if I were looking at the square root of 1 minus t, the domain of that particular function is going to be the set of all t that is less than 1, because if the value of t is less than 1, then the function will be defined. If t is greater than 1, we will have negative values inside of the square root. And likewise for h of t, since we're considering the function t, the domain of this particular function is clearly going to be negative infinity to infinity. If you need to, draw each of the domains in the same number line, so that for f, we know we're going between 0 and infinity. For g, we know we're going between 1 and negative infinity. And for h, we know that we're going through the entire number line. Where those all intersect is in this region right here, between 0 and 1. And so the intersection is going to be the following. And it will give us that the domain of R is 0 to 1 inclusive. Sometimes when sketching our graphs of plane curves, it is not obvious that the curve represents a particular shape. Sometimes we have to do a little bit of algebra in order to ascertain what the shape is going to be. And so, for example, if I were given the vector valued function r of t is equal to 2 cosine of ti minus 3 sine of tj, I'm going to put the restriction that t is between 0 and 2 pi, and I want to sketch the plane curve. And this is the curve that the vector valued function is going to traverse. So we're given that x is equal to 2 the cosine of t in this case, whereas y is equal to negative 3 sine of t. And it's, as I said, it isn't clear what the function actually is. However, if we were to solve for the cosine and sine respectively, we would get that x over 2 is equal to the cosine of t, and y over negative 3 is equal to the sine of t. Squaring them, we would find that x squared over 4 is equal to the cosine squared of t, and y squared over 9 is equal to the sine squared of t. We can add both of these functions together in order to eliminate the parameter altogether. And what we get is that this is the graph of an ellipse. Whose major axis is the y-axis. The only difficulty that this poses is that remember that all plane curves have a specific direction. And so we're going to still have to ascertain the direction, but this is done in much the same way as was done in the previous examples. That is, that we would have to choose values of t in order to determine x and y. I suggest sticking with simple values of t and seeing what happens as t increases. So for example, if t is equal to 0, we find that we're at the point 2, 0, which of course is this point right here. And if we're at the point pi over 2, then we're at the point 0, negative 3, which means that we've come down and we are traversing the curve in the clockwise direction. This is important because as we start inserting our vectors and we want to understand how our vectors are going to go and traverse the curve in the direction that the curve follows. And so that's going to be in this sort of clockwise direction. One important example in 3D or in 3 space that we have is that of a helix, which has the same shape starting with a circle. In this case we have a circle of radius 4. But which is elevated as t is increasing. So we know that this is going to traverse the path of the circle x squared plus y squared is equal to 16, and so we're going to have a circular path that is traveled. However, the main difference is going to come with the fact that we also have to take into account the t. So while on the xy plane, we do indeed have a circle, we have to remember that that circle is brought about through an increasing value of t. And so the end result is going to be a graph starting from the point, if we were to start at the point 0, would then end up lifting off the plane and spiraling upward. Our vectors from the vector valued function would traverse the curve as it travels along that path. This graph is called a circular helix, which is more or less a spiral. In calculus, though, we have a few main questions about these particular functions. Our analysis of the functions requires us to understand how to evaluate particular limits, number one, and then whether or not we can determine anything about the continuity of the functions. With functions in one variable, this was a very simple task. However, as we start to increase the complexity of our functions, this does not become as straightforward. So let's turn our attention now to limits and continuity. Let R1 of t equal F1 of ti plus G1 of t j, and R2 of t is going to equal F2 of ti plus G2 of tj. This also holds in R3 in much the same way, but for simplicity I will do it in R2. If you were going to add the two vector valued functions together, this is adding or subtracting, you would do it component-wise just as you had done previously. And so you would add the x components together, and the y components together. You could take dot products of the two, and in which case you would get F1 of t, F2 of t, plus G2 of t, G1 of t, G2 of t. Cross products likewise could also be taken of these, as well as scalar multiplication. We therefore give the following definition, that if we were given a vector valued function, and we'll do this generally now, in R2 and R3, the same thing is going to hold, that the limit as t approaches a of r of t is going to necessarily mean that I am going to take the limit of each of the individual functions, but the component is going to remain the same. And if you had a k component, it would be similar. You would tack on the k. What we are saying, and what was said when you found limits for the first time in Calculus 1, is that the distance between the limiting value of f and or of g is getting closer and closer. That is to say, in our case, that if we're considering distance, we're actually considering the norm, or the Euclidean norm, between r of t and some vector L, which is the limit of our function, and that this distance is getting closer and closer to 0 as t is made closer and closer to a. As the distance between t and a gets close, the Euclidean norm, which is the distance between 2 points in R2 and R3, is getting smaller. And this is an important distinction between vector-valued functions and just regular real-valued functions, that we now change the way we conceive of distance in this particular space. In essence, if we were to consider, let's say, this curve right here, we can understand what is going on between the two. For example, if we were to have our limiting function here being L, and our vector-valued function being r of t, if you were to try to sketch the difference between the two, the difference between the two functions would be the following vector, starting from the L and heading towards the r, so that my vector-valued function here would look as such. If r is made closer, now to L, we can see that now the distance is going to be smaller, and so that the Euclidean norm is going to be smaller. And it's important that you understand that what we're describing here is the magnitude of the resultant vector between r of t minus L. This becomes essential for us to understand the concept of differentiation of vector-valued functions. And so we would define the derivative now, r prime of t, to be the limit as delta t approaches 0 of r of t plus delta t minus r of t, all divided by delta t. You could also describe it as the limit as t approaches a of r of t minus r of a, all over t minus a, and that would be the derivative at a specific point. Necessarily, this is going to mean the following, that since r comes in components, and I'll do this in the case of 2 space, but it is true also in 3 space, that we get the following. We'll get the limit as delta t approaches 0 of f of t plus delta t minus f of t all over delta ti plus the limit as delta t approaches 0 of g of t plus delta t minus g of t all over delta t, j. And so simplifying this expression, we would end up with f prime of ti plus g prime of tj, which means that in order for us to differentiate a vector-valued function, we need to differentiate each of its components individually, and it will create new components that are derivative functions as well. And of course this holds in R3 as well. This all is provided, though, that f and g are differentiable. Please note that I have omitted some details in between here that you should be able to fill in using the material that has been discussed previously in this lecture. Pictorially, what does the derivative represent? And to generalize this picture, I'll do the picture in 3 space, although the same is true in 2 space. So let's actually draw it in 2 space and say that the same is in 3 space. 2 space is always going to be much easier to depict than 3 space is going to be. So if I have some vector valued function here, and I have the following. I have r of t so this is r of t, and then I have r of t plus delta t, which is going to be the vector valued function shifted over. As I make their difference smaller, the resultant vector that is going to ensue is going to be a vector that is tangent to the curve at t. Between, of course, in between here, we have our difference between r of t plus delta t and r of t. Now, when is a function differentiable? Differentiability, remember, is a commentary on the smoothness of a curve. And so we need to understand that that a curve, so it is said, a plane curve or a curve defined by r of t is said to be smooth, provided f prime, g prime, and if there is an h, and h prime are continuous on I, and that r of t does not equal the zero vector for any t and I. And the reason this is important for us, we can understand in R2 why this becomes important for us to understand. This should be r prime, I'm sorry, that r prime does not equal 0. It is important for us to understand that r prime, it cannot equal the zero vector, because if we're looking at r prime of t as being f prime of t, g prime of t, remember that in order for us to define a tangent line, or the slope of the tangent line, remember that the slope of the tangent is going to be given by dy dx. And so right here we have dx dt, and we have dy dt, and we know from parametric equations, perhaps in calculus 2, that if I want to find dy dx, that's going to be dy dt divided by dx dt. And if this is equal to a 0 over 0 form, this implies that dy dx does not exist. And this will correspond to a sharp point or a cusp. What we would say in engineering terms is that this is some form of roughness to the curve. And so when dy dx is not a continuous function for t, then we end up with a rough curve. So in order for us to be able to determine where a function is differentiable, we need to determine where the derivatives are going to be equal to 0. And exclude that particular value. We have a few rules for differentiation, so properties of derivatives. And most of these are extraordinarily intuitive to you, although they can be proved. That if I were to take the derivative of a constant times r of t, of course, you would extract the constant and find the derivative of r of t individually. That goes by linearity of derivatives. If I were to take the derivative now of the sum or difference of two vector-valued functions, I could find the derivatives independently and add and subtract them. If I were to have a scalar valued function, w of t, times a vector valued function, the derivative there would be w of t times r prime of t plus w prime of t times r of t. And this is where w of t is a scalar valued function. Of course, if we had two vector-valued functions, r of t dotted with u of t, their derivative would be what you expect. That is, that r prime of t would be dotted with u of t, and that u prime of t would be dotted with r of t. The same would hold for a cross product. So that if you would do d dt of r prime of t cross with u of t, you would end up with r prime of t cross u of t plus u prime of t. Sorry. Order does matter in this particular case, so then this would be r of t cross u prime of t. If you had a vector valued function composed with a scalar valued function, you would find r prime of w of t multiplied by w of t. And lastly, if you had that r of t dot r of t is equal to a constant, remembering that what r of t dot r of t is going to be, it's going to be the norm squared, then d dt of r of t dot r of t is going to equal 0, which is what you would expect. Integration also follows a similar path. That if we let f and g be continuous on AB, then we would integrate r of t component-wise, so that we'd have the integral from a to b of f of t dt times I, plus the integral from a to b of g of t dt j. And the same, of course, would hold in 3 space. We conclude with the following example. Differentiability and understanding where it occurs is very, very important. Determine if the curve C parametrized by r of t equaling 1/3 the sine of t cubed j I plus 2j plus 1/3 the cosine of t cubed j, for t being in negative pi over 4 to pi over 4, is smooth. In other words, is it differentiable? In order for us to determine if it's differentiable, we have to determine where the curve is going where the derivatives of each of the functions of the curve are going to equal 0. That is to say, we have to prevent r prime from equaling 0, the 0 vector. And so we necessarily are going to have to find r prime of t. So note that r prime of t in this case is going to equal the sine of t, the quantity squared, times the cosine of t, I, plus 0j, plus the cosine of t squared, minus the sine of t, j. And we notice that in each of these cases, that r prime of 0 is going to give us 0. And so therefore, at the 0 vector. And so therefore, at t is equal to 0, r is rough. There's going to be a cusp of some sort, or a lack of smoothness. Which means ultimately our function is not differentiable at t equals 0.